In recent lectures, we discussed the key rotational concepts of torque and angular momentum. We're now ready to describe how these ideas come together to characterize changes in rotational motion described by our third fundamental principle, the angular momentum principle. Let's start by noting that the momentum principle and the angular momentum principle closely parallel one another. Recall that the momentum principle, which for the types of translational motion we've studied is the same thing as Newton's second law, relates changes in the translational motion of our system to the interactions of the surroundings with our system. So, for example, if we're able to specify the total pushes and pulls, the total force, the net force exerted by the surroundings on the system, then we can use the momentum principle to predict the motion of our system. Or, as we have also seen, if we're able to observe and to measure the motion in a way that allows us to describe how the motion changes, then we can use our momentum principle to determine the net force acting on the system. The angular momentum principle also links changes in motion. In this case, changes in rotational motion described by the change in the system's angular momentum to the interactions of the surroundings, in this case the total twists, the net torque exerted by the surroundings on the system. So if we're able to specify the net torque on our system, we can then use the angular momentum principle to predict the rotational motion of our system. Or, if we're able to observe and to measure the rotational motion in a way that we can describe the changes to our system angular momentum, then we can use the angular momentum principle to determine the net torque from our surroundings acting on our system. Let's do a few examples to see how this plays out. We'll start once again with the system of a particle of mass m that rotates on a rigid rod of negligible mass. This rod is fixed at one end so that it rotates about an axis we'll label as A. Let's say that when we first observe the system, the particle is located with respect to A by the position vector r sub A, and that the particle is moving with momentum vector p, as shown. Let's apply the angular momentum principle to predict the angular momentum a short time delta t later. First thing we'll do is to compute the initial angular momentum, L sub I. That's just the cross product of r sub A with p. Recall that earlier we discussed that for the case of rigid rotation like this, the mass must move in a circle so that the vector momentum p is perpendicular to r sub A. So the magnitude of the initial angular momentum is just the product of the magnitudes of r sub A and p. By applying the right-hand rule, we find that the direction for the initial angular momentum is out of the screen for this example. Now to predict the new angular momentum, L sub f, a short time delta t later, the angular momentum principle tells us that we add to the initial angular momentum, L sub I, the product of the net torque, tau sub net, and delta t. So we need to specify the total twists, the net torque on our system. Let's say that the net torque is 0. Then the angular momentum principle tells us that the final angular momentum, the angular momentum delta t later, is equal to the initial angular momentum. In other words, the magnitude of the final angular momentum is the same as the magnitude of the initial angular momentum, in this case the product of r sub A and p. And the direction of the final angular momentum is the same as the direction of the initial angular momentum, in this case out of the screen, in the plus z direction if we take the plane of rotation here to be parallel to the xy plane. Now it's worth noting a couple of things here. First, in this case, the position vector and the momentum vectors are, in fact, changing. They're both changing directions as the system rotates. However, the angle between the vectors and the vector magnitudes don't change. The mass m moves in a circle at constant speed, so the angular momentum magnitude doesn't change. Second, notice that since the momentum is changing directions, the net force on m is non-zero. Moreover, we know from our earlier work that since m moves in a circle at constant speed, the vector dp dt points toward the axis A, and so too must the net force. The torque due to this net force is r sub A cross F net, and since all of F net is aligned with r sub a, there is no component of the force perpendicular to this position vector. Or equivalently, in this case, the angle between F net and r sub a is pi, and sine pi is 0. Then r sub a cross F net is 0. So we see here an example where the surroundings act in such a way as to exert a zero net torque and a non-zero net force on our system. In this case, it's the rod in the surroundings that acts on our system, the mass m, in this way. Now, how would our prediction for the final angular momentum change for this system if there was a non-zero net torque? Let's start with the same initial angular momentum as before, so that when we do the cross product, we find the same magnitude and direction for L sub I. However, now we're going to imagine that the rod exerts a net force, F net, as shown, where the angle between the position vector and the net force is theta. And in this case, it's greater than 0, in fact, greater than pi over 2 here, and less than pi. We can compute the net torque, tau net, from the cross product of r sub a and F net. The magnitude of the net torque is the product of the magnitudes of the position vector and the magnitude of the net force times sine theta. The right-hand rule tells us that the direction of tau net is into the screen, in the minus z direction. So in this case, the angular momentum principle tells us that the final angular momentum, L sub f, is not the same as the initial angular momentum. To find the final angular momentum, we add the product of the net torque times delta t to the initial angular momentum to find the final angular momentum. Notice that all these vector quantities have non-zero components along the z direction only. So we can write out the z component of the angular momentum principle like this, where we use the fact that the z component of L sub I is positive and the z component of tau net times delta t is negative. Notice that L sub f could point either along the plus or minus z direction, depending upon the values of theta, delta t, and the magnitudes of r sub a and p. Let's practice the angular momentum principle on a different example. We'll do this by starting out with the following clicker question. A ball moves in the xy plane with a momentum represented by the red arrow as shown. What is the ball's z component of angular momentum about the axis at A? Let's compute the angular momentum r sub a cross p for this example. First, using the right-hand rule, we see that the direction of the angular momentum is into the screen, in the minus z direction, so that we can rule out all answers that are non-negative. Now, the magnitude of the angular momentum can be found by recognizing that the moment arm, r perp, can be read off directly. It's 4 meters. So with that, plus knowing the magnitude of the momentum, we find the magnitude of the angular momentum is 40 kilograms meters squared per second. And so the z component of the ball's angular momentum is minus 40 kilograms meters squared per second. Let's take this as the initial angular momentum of the ball, which we choose as our system. Let's apply the angular momentum principle to find the ball's angular momentum delta t later. We know that we need to specify the net torque, so let's consider the case where the particle shown is free. There is no net force acting on the particle. In this case, this means there is no net torque. Tau net is 0, and so our angular momentum principle tells us that the final angular momentum, L sub f, is the same as the initial angular momentum for any time interval delta t later. Notice in this case the particle keeps moving along a line parallel to the y-axis. And notice that while the position vector r sub a changes, the moment arm does not change. And since the momentum vector doesn't change, the angular momentum is constant. Now let's modify this example by imagining that our ball is falling near the surface of the Earth, where we use our typical coordinate system with the y-axis oriented vertically. Let's also assume that the ball's mass is 2 kilograms. We'll keep everything else the same as in our previous example. Let's apply the angular momentum principle to predict the final angular momentum at time interval delta t later. First, we need to answer this clicker question, which asks us to find the net torque on the ball about the axis A. Here's the solution. The weight of the ball is the net force on the ball. The weight points downward and has a magnitude equal to m times g. By extending the line of action of the weight, we see that the moment arm is, once again, r perp. So we can readily find the magnitude of the net torque, m times g times r perp, which in this case is 80 Newton meters. We apply the right-hand rule to find the direction of the torque, and in this case we see it is into the screen, so that the z component of the net torque is minus 80 Newton meters. Now we have everything in hand that we need to predict the final angular momentum of the ball. Let's do that now for a specific delta t, say 0.05 seconds later. See if you can do this. Here's the solution. The only non-zero components are the z components. So to find the z component of L sub f, we take the sum of L sub i's z component, which, as we found earlier, is minus 40 kilograms meters squared per second, and add tau net, the net torque, times delta t. And we find that L sub f, the final angular momentum, has a magnitude of 44 kilograms meters squared per second, and the direction of L sub f is in the minus z direction. We are now going to turn to examples where we apply the angular momentum principle to multi-particle systems. We'll do that beginning in our next lecture.